So we need to look at the oscilloscope screen. Okay. Okay. This is optical fiber. One box, or what we say, one reel of optical fiber, and the length is about 1 kilometer. 1 kilometer. This one is 2 kilometer. And we are going to measure the length of the fiber. So how are we going to do the measurement? Do we open this up and measure with ruler? Cannot. So what we do is that we're going to hook up this fiber to a light source and a photo detector. Okay. So here we are using an LED light source, infrared light source, and we plug this to the oscilloscope to see the waveform. So what happened here is that we modulate the LED. That means LED, as in like if you do direct current, it's a flat line, right? So now we apply sine wave to it. So what happens is that the light coming out will be oscillating. Okay. So the light that exits out from this point and exits out from the source and exit from the end of the fiber, the phase should be the same. So that's what the theory is given. So what we are going to do is that when we look at the oscilloscope screen, so we're going to fine tune the frequency. So what do you see? All the waveform is moving, right? Yes. Or is it everything is moving? What do you see when I change the frequency?
No movement.
Something is not moving, right? So these two are not moving, right?
Yes.
So if you were able to determine the time difference, because this is an oscilloscope, so the axis here is time. So if you can determine the time difference here, and you plug in the equation, plug this value to the equation, then you can find the length of the fiber. So of course we need to know the refractive index of the fiber. Well, this is given in the manual. All we need to do is to find the time difference where the light enter and exit through the fiber. So this is one trick that you can use. Alright? Okay, any questions?
Any questions?
Question.
Tanya lah.
No.
So for computer experiment, what's the apparatus that we play? This polyvariable.
Okay. So this experiment actually, this setup over here actually contains, you can do a lot of sub-experiments. So firstly, we will ask the student to hook up the fiber from either LED or laser and then hook it up to the photo detector. So we want to know what is the difference between the LED and laser. So you know that LED, if you increase the current, by the way, the variable here, the dot that you see over here is controlling the current. So we know that current, if you increase the dot, then the current will increase, and then of course the power will increase a lot. For LED, the power and the current, they have a somewhat linear relationship. But for laser, it's different. For laser, when it's at a very low current, it behaves like an LED. But when it passes through a threshold current, then lasing occurs, and here you will be able to measure a huge increase in terms of power. So the graph is not linear anymore; it's something like this, and this is like exponential, like your diode. Okay. So the student will need to determine the bias point from there, from the obtained results. And then the next one is to use the bias point, and we do a series of experiments. Now, one of the experiments is that we want to know the loss in the fiber. How are we going to know the loss? Now, in the manual, it is given that the formula of the loss is actually very simple. If you know the power here and you know the power here, then done. You apply it into the formula. But the thing is that you don't know the power here. So how are you going to do that? So herein, we're going to use a short length of optical fiber, and then we're going to plug the fiber in series with this one, and we will be able to determine the overall loss. And then we repeat the experiment with the short length of fiber, and then we can be able to tell the small losses there. So using the two values, we can determine the loss of the entire fiber reel.
Oh.
So aside from this one, in terms of optical communication, yes, now we go through the much more practical, much more important part is that we know that light, when they propagate across a fiber, the intensity will drop, right? The question is that how much length that it is needed to see all of the light intensity drop to zero. So we can use this one to simulate a condition where we can do a bit of calculation and then we'll be able to find the what we call the attenuation limit length of the fiber. Every optical fiber is made of different kind of materials. For this one is I think it's a mix of silica and germanium. So it's not germanium, it's germanium oxide and silicon oxide. Mostly it's silicon oxide. Okay. So there is a limit where light can propagate across. So we want to determine that one. So once we know that one, we will do another experiment that is to find the dispersion. Now imagine this: you have an optical fiber. You input your data in. Data, as we can imagine, is binary 1010. So you don't want your data going into the fiber and its exit, it becomes something else, right? So we need to keep the data shape of the house to be somewhat consistent. So we need to do a little bit of investigation. So what we do is that we're going to change this one into square wave. And then we're going to measure the rise time. So if you know the rise time, you know how fast the signal rise from low state to high state, then that will give you an idea of what is the frequency limit or the bandwidth of this fiber can sustain. So for that, I think that covers most of the aspects of the fiber. The fundamentals. All right.
All right.
So any other questions?
Can you repeat how it's supposed to measure the length of the
Optical fiber. Okay. So we have one formula. The length of the fiber is equal to speed of light multiplied by the time difference divided by refractive index. So the important parameter here will be the time difference, delta t. So what we do is we will use a sine wave. Okay, we'll use a sine wave to modulate the light signal, and when we vary the frequency, we can see that there are two static points. So this static point representing the phase of the waveform that is entering and exiting the optical fiber. They should be the same. So once you determine the position of the static point, you calculate the time difference, which it can be done using an oscilloscope. So you can see there's a delta t over here already. We set it already. And you plug the value into the formula, and then you can get the length of the optical fiber.
So in order to calculate the length of the optical fiber, we need to know whether it's in phase or not. If for instance the light is not in phase, you can calculate the length of the
Okay, now if it's not in phase, we can see clearly when we adjust the frequency here, because all the time we assume that the phase in the sine function is fixed, right? But now we're going to change it slightly a little. This is to filter out which one is not in phase. So you can see the one that is moving is out of phase, while the one that is fixed is in phase. So that is where we need to look at. Right?
Understand.
Okay.
All right. Thank you.
Thank you.